In this video we will discuss the time complexity of AVL tree. Time complexity of AVL tree and how it is better as compared to the normal binary search tree when it is unbalanced. What is the benefit of a balanced, highly balanced AVL tree as compared to the unbalanced binary search tree, that we will discuss with the help of time complexity. Now suppose this is a perfect binary search tree and AVL tree as well. Perfect binary search tree and AVL tree as well. Okay, we can expand it more. This is an example of complete and perfect binary search tree, and this is an AVL tree because all the nodes are having the balance factor 0. Okay. Now, suppose number of node at hth level is equal to number of node at h minus 1th level plus number of node at h minus 2th level plus 1. This is approximately true for all the cases. For all the cases, this is approximately true. So now if I expand this one, then it becomes n h minus 1 again as a recurrence relation. If we apply them, n minus 2 plus n h minus 3 plus n h minus 2 plus 1 plus n h minus 2 plus 1, that we have is equal to 2 into n h minus 2 plus n h minus 3 plus 2. Clearly, as 2 is a positive constant, positive non-zero constant, so clearly we can say nh is greater than 2n h minus 2. This can't be negative, number of nodes can be negative, and 2 is a positive number. So taking this 2 is a positive, definitely the value of these 2 will be positive. So definitely nh will be greater than 2 into nh minus 2. And as per the rule of the tree, binary tree, we know that 2 into, as we know, 2 into n h minus 2 is equal to 2 to the power h divided by 2. 2 to the power h divided by, when h is the height, n is the number of nodes. 2 into n h minus 2, h minus 2th height, the number of node at h minus 2th height multiplied by 2 is equal to 2 to the power of height divided by 2, half of the height. So this is true for the binary tree. So we replace it, we get, replace it, nh is equal to, nh is greater than 2 to the power h by 2. So taking log in both the sides, making log in both the sides, what we have, log of nh is greater than log of 2 to the power h by 2. So now from here what we have, log nh is greater than 2 h by 2 into log 2, h by 2 into log 2. And as this is a binary operation, as this is a binary tree is a binary operation for searching, inserting and deleting elements is almost a binary operation. So the default base is considered to be 2. The default base of this log is considered, absolutely considered to be 2. So we can say log 2 base 2 is 1, but we know log 2 base 2 is 1. So we say log nh is greater than h by 2. H by 2. From here what we can write, h is less than 2 log nh. H is less than, the height is less than 2 into log nh. Height is less than 2 into log nh. So approximately, by approximation we can say the height is equal to order of log nh. Order of log nh. The height equal to order of log nh. And height means the number of edges it will pass. The number of edges are required to be passed to reach the last level. So height and time complexity to insert an element, delete an element, searching an element from the bottom of the tree will be almost synonymous. The height of the tree and the time complexity of accessing any element, deleting any element or searching any element will almost be same. So the time complexity will be order of n, order of log n, log h. Now, the time complexity of AVL tree is order of log nh. Now suppose if I consider the case of a worst case of binary search tree, unbalanced binary search tree where the elements are in ascending or descending order. So it will be stored in a binary search tree more like a linear data structure or linked list like this. Suppose we have 10, 20, 30, 40, 50 like that. So it is increasing order, a specific increasing order. So it is stored in a BST in a linear order, sequential order. So 10, 20 is right of 10 because it is greater in value as compared to 10. 30 is greater than 20. So it is right of 20. In this way, it will be organized. What is the time complexity of it? In best case, it is 1. If it is the first, worst case it is the n, order of n. So time complexity will be order of n, O(n). Because the n number of 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 steps we have to go to reach to the last level. To search an element, to insert an element, to delete an element from the last end. So we have to go to n steps. So time complexity is of order of n. And here in AVL tree, the time complexity is the order of log n. Time complexity is the order of log n. And we know that log n is less than n for n is greater than 2 or more. When n is greater than 2 or more, the log is n is greater than 2, and as n goes higher, the difference between n and log n will go higher. Because log n is less than n. As n goes higher, log n will be log nh will goes higher and higher as compared to n, lower and lower as compared to n. So value of log n at hth layer go lower and lower as compared to n. The log n, you can say generally log n. Log n is go, log n becomes lower and lower as compared to n as n goes higher, as number of nodes goes higher. Okay, as for a lower n, suppose n is 1, so definitely log n equal to 0. The log n equal to 0 and n equal to 1. For n equal to 2, the log n equal to 1. For n equal to 2, log n equal to 1. For n equal to 3, log n equal to 1 point something. For n equal to 4, log n equal to 2. If the default base is 2, always keep in mind that default base is always 2 for in this logarithmic analysis, because this is a binary tree analysis. So the default base has to be 2. Now log n less than equal to n. As n goes higher, so we get a better time, less processing time in AVL tree. This means a better time complexity we are achieving in case of the binary search tree. In case of the AVL tree as compared to unbalanced binary search tree. Suppose an example we can make clear the inserting the elements in a AVL tree. How the elements are inserted in the AVL tree, by which method, and how many rotations are required. Suppose we are going to insert an elements in an order that is given. Okay. In a given order, if I insert the elements in a binary search tree, and how they can be converted into a AVL tree, how many rotations are required, that will be discussed in example. Now the example is, this is an example. 6 elements are there. Suppose we want to insert in the same order. First of all, 30, 60, 50. 30 is, we have inserted 30. 60 we have inserted right of 30. It is greater than 30. 50 inserted at the left of 30. 60. So 50 is inserted. Okay. Now this is right left. Right left unbalanced. So we have to go for the rotation. Accordingly we have to We have to apply the rotations to make it a balanced AVL. This part, balanced AVL subtree we have to make. Suppose this 50, we are starting with this. When there is a left, we have to go for the clockwise rotation. This means clockwise rotation, as we discussed in the last video, the clockwise rotation. So by doing so, we can get, first we have to convert it into the RR unbalance. First we have to convert it into the RR unbalanced tree. So RR unbalanced, it will be converted 30, 50 and 60 in this way. You can arrange it 30, 50, 60 because it is not a 50 will replace 60, 60 will come down. So like that, it will be RR. And after that, as we know, for RR imbalance, in the last video we have learned, we have to go for only one rotation, and that is the anti-clockwise rotation, that is the left rotation. First of all, we have applied the right rotation. So right rotation 1 and left rotation, right rotation 1 and now left rotation. Now the left rotation is anti-clockwise rotation, keeping 50 fixed. 50, 30, 60. First three nodes we have made them balanced. Left 1, right 1. Total number of rotations so far: right rotation 1, left rotation 1. Now the next value 90. Where we place 90 and 25? 25 we can place here and 90 we can place here. Now let's see, is there any unbalance? The incident of non-balancing factor. What is the balance factor of 25? 0 minus 0, that is 0. Left subtree the height is 0, right subtree the height is 0, so it is 0. What is the balance factor of this? 1 minus 0, 1. What is the balance factor of this? 2 minus 2, 0. What is the balance factor of this? 0 minus 1, minus 1. What is the balance factor of this? 0 minus 0, 0. So it is completely balanced AVL. It is completely balanced AVL so far. Now let's insert 7 here. Now let's insert 7 here. 7 is less than 25. So let's insert here the 7. So as we inserted 7 here, so what will be? This is balanced. This is 1 minus 0 balanced. This is 2 minus 0. That is not balanced. That is not balanced. This is also balanced, but this is not balanced. So this is balanced because the height is 1, 2, 3 and this right height is 2. 3 minus 2 is 1. So this is falling under this range, minus 1, 0, plus 1. But this is not falling under that range because the height of the left subtree is 2, height of the right subtree is 0 because there is no node underneath in the right side. So it is 2 minus 0, that is 2. 2 doesn't fall within this range. So we have to make it balanced. This part, this subtree we have to make balanced. How to make balanced? This is a LL means a clockwise rotation. So what we have to do? A clockwise rotation. Only this. We have to make a clockwise rotation. As we find, only this part we have to make a clockwise rotation. Only this part. So clockwise rotation by moving 30 here, 25, 37. Only this part. That's subtree. So we have to make this. Now finally what it comes? Finally, how many rotations are used? Now here 1 right rotation, right 1, 2 right. There is no left rotation. There is no left rotation. No. 1 left, 1 right, then 1 right. So 2 right, total 2 right rotations and total 1 left rotation. Only 1 left rotation, 2 right rotations required to insert these elements in a binary search tree and balancing them to convert it into AVL, height balance tree. So finally it becomes, the tree becomes 50, 25, 7, 30 and right of 50 is 60 and 90. These all nodes are balanced. All nodes are balanced. All nodes are satisfying the range of the balance factor. So this is an example of inserting a node in a BST in a AVL manner so that they can be height balanced AVL. So number of rotations required is right rotation 2, left rotation 1 in this case. Thank you. Thank you so much. In the next video we will go into depth of another topic of binary tree or other trees. Thank you.